Okay, hello, good afternoon. Welcome to the next Warsaw University Astronomical Observatory Tuesday seminars. And today we have Dr. Martyna Chruslinska, who was our student here. She did her bachelor degree here with Tomasz Bulik and then her master with Chris Belczyński, and then she went to the Netherlands and did her PhD there, and now she's a postdoc at MPA in Garching, Germany, and is going to tell us about gravitational waves in the context of galaxies and binaries. Welcome. And Martyna,
Thank you so much. Okay, good afternoon, everyone. Here in the room as well as online. I'm happy to be back in Warsaw. As you can see, the shortest title that I could come up with for this talk is a fairly short one. But I'm going to focus on how the two first topics, so galaxies and binaries, connect in the field of gravitational wave astrophysics, which itself is a field that really exploded following the first direct gravitational wave detection in 2015. And until now, we have detected about 100 of astrophysical gravitational wave signals. So this is already enough to study statistical population properties of those sources, and it's only the beginning. Our detectors are still improving, and the next observing run that is going to start next week is going to at least double this number. So you can see the number of detections is quickly running out of this slide. And even better, with next generation detectors, we are going to see a comparable number of signals to those that we have now per day. So the size of the sample is definitely not a problem here. And gravitational waves are also not obscured by dust, and we have a fairly good understanding of the associated observational biases, meaning that in this field we do not have to deal with the factors that are common limiting factors in the case of electromagnetic observations. And one more thing here that I'm excited about is that those feature detectors are going to be sensitive enough to see sources that are extremely distant. We could say they are in the early universe. But let's start with the sources. So gravitational waves that we are able to detect now come from black holes and neutron stars that are orbiting each other very close, so that they almost touch what we call a merger, and that's when we can observe this strong gravitational wave signal if the source is close enough. So those are very tight binaries that are made of afterlives of massive stars. And this link to massive stars is actually one of the reasons why many people, or astronomers at least, got excited about gravitational waves. Because we know that such stars are intrinsically rare when we think about the IMF, and they are also very short-lived, which is enough to make them difficult to study, but they are at the same time extremely important. They are the ones that are responsible for the ionizing radiation and actually the bulk of emission that we see when we look at distant objects. We link them to some of the most energetic transient events that we can observe, and they also drive chemical evolution. So through all that, they can affect lives of entire galaxies. Now we also know that massive stars are commonly found in binaries or in stellar multiples. So they typically have at least one nearby stellar companion with which they can interact by exchanging mass and angular momentum. And this means that they typically have a rather complicated evolution. However, some of such binaries can produce observable gravitational wave sources, but we know that this is not a common outcome of evolution. So you can see the problem in this slide. To be potentially observable to us, the black hole neutron star binary needs to merge within the time that is at least not longer than the age of the universe. And for this to happen, the required separation at which we need to have two double compact objects needs to be tiny compared to radii that massive stars reach during their evolution. So this means that something special needs to happen to produce a gravitational wave source. we can't just start from 2 regular massive stars already at the desired orbit of 10 or 3 solar radii, because such stars would just eat each other as they evolve and expand and never produce a double compact object. And there are different ideas about how to overcome this issue. They are called formation channels. And actually, all I'm going to say about this topic in my talk is that it will be biased towards what we call isolated channels, so where we at least do not need to involve dynamical interactions to bring 2 compact objects close together. And in those channels, we bring stars or their remnants close together through various phases of mass transfer in late stages of binary evolution. So to simplify things, this will be about a binary channel to form gravitational wave sources. And what I want to stress with this slide is that even though black holes and neutron stars form quickly after the formation of their parent stars, they do not necessarily merge quickly in binaries. And this delay between the star formation and the merger depends on the properties of the binary, on its exact formation history. So this is something that will be different for different systems, and in principle, it can be arbitrarily long. So this means that the population that we observe with gravitational wave detectors, probing a certain volume around us, is always a mix of systems that formed at different times in different environments. And it also means that, we have to remember that those systems are themselves part of a much bigger environment that is itself changing. And it's changing on much longer timescales than massive stars, but actually comparable to what we need to think about when we're dealing with double compact object mergers. And what's important here is that the composition of matter that is filling galaxies is changing. As next generations of stars evolve, produce heavier elements in their interiors, and then they enrich surrounding medium, so that next generations of stars form from material with a bit different composition. And that's the environmental effect that I'm going to focus on in my talk. So I'm sure you're familiar with this example, right? Well, we compare 2 stars that formed at different metallicities, but are otherwise identical. Then one of the main differences between them is the mass loss that they experience through radiation-driven stellar winds. So the mass loss is lower at lower metallicity, which allows the star to retain more mass as it evolves and potentially produce more massive compact object, more massive black hole. So that's one of the ways in which the remnant can retain some memory of the formation metallicity. Now, this is of course not so straightforward when we're dealing with binaries that can exchange mass, so the link is more less straightforward. And this is just one example of the effect of metallicity on evolution. But it is the most straightforward one and possibly the most important one. And it's a pretty significant effect. So we have to remember about metallicity when we build a model population of gravitational wave sources, but actually also any other stellar origin transients. And we want to build a population that can be compared with the observed one. And I like to think about this modeling as a 2-step process where we need to combine 2 very different ingredients. The first is what I call a metallicity-dependent cosmic star formation history. So it's a quantity that tells us, that describes the number and metallicity of stars that formed at different times. And once we know this, we can describe how those stars evolve, how they interact with each other, and what's the core collapse physics, and many other things that we need to account for before we find out how many of those stars that formed across the universe produce mergers, when those mergers happen, and what are their properties. And my recent work is heavily focused on this first part, not necessarily in the context of gravitational wave astrophysics, but I'm going to focus on this today. And I will use a few examples to show you why it's important. And for this, I will focus on the properties of black hole mergers that can be probed with gravitational waves. such as the merger rate density in the local volume. So that's the simplest quantity. In principle, it's just one number, but we already have nice constraints on it. And what you can see here is that when we compare the estimates of this quantity that were recorded in different studies, that here is spread vertically, then you can see that altogether this covers almost 4 orders of magnitude. There are also those green dots within each horizontal bar, so they show values that people obtained when they were considering variations of assumptions that describe how massive stars evolve and interact in binaries. So you can see some of the main stages that the binary needs to pass through to produce a double compact object. And many of those stages are actually separate areas of research, and many of those are uncertain. However, when we want to build a population model, we need to simulate many binaries. So we need to often very much simplify very complex processes and collapse those 4 areas to one parameter. But it's common to do parameter studies to see at least how different assumptions affect the result. And as you can see, they can affect them a lot. But the good thing is that when I plot current gravitational wave constraints on top of those results, so this purple bar, then you can see that this is a much narrower range than what is found by the models already, which is great, because in principle, it allows us to rule out many of them. But unfortunately, we cannot say that we have just learned something about the evolution of massive stars. And in fact, the interpretation of this result is rather unclear, because we have to remember about this first part of the modeling, where we need to describe how the universe is producing stars. And almost every group listed here made a different assumption, used a different way to describe this. And here, what you can see here is a selection of those assumptions that were used to describe precisely the rate at which the stars are forming at low metallicity as a function of loopback time. So this is like a low metallicity version of the Nadal plot. And what I want you to notice is that this is a fairly wide range of fairly different assumptions. And for now, I'm just going to pick 2 extreme ones from here. So the one that tells me that basically all the low metallicity star formation happened more than 10 gigayears ago, and the one that says that, well, such stars are forming at a very non-negligible rate even now in the local universe. And I will ask, what does it mean for the black hole merger rate? So now it's plotted as a function of time, so not only the local value, so you can see how it evolves according to the model, and well, you can see 2 lines, they are fairly different. They show different evolution, you have to pick at different locations, and they differ in normalization a lot. So it clearly shows that this is an assumption that is important for the result. And you can also notice that with the same treatment of stellar evolution, we either satisfy constraints or not, depending just on the metallicity dependent cosmic star formation history that was used. To make this worse, well, there are many ways to fit models inside this box for now. So different combinations of assumptions about stellar evolution and about the way the universe is producing stars can lead to similar outcomes. And I did not really even consider the dynamical merger formation channels here. So I would say this is a pretty serious problem for the interpretation of current population properties observed with gravitational waves. And I'm going to leave it like this for now and focus on another question. So actually why this is so sensitive to metallicity. And I like to show this sketch here. So this figure summarizes the main characteristics of what is a commonly found dependence of the efficiency of formation of black hole mergers as a function of metallicity. So this tells us that black hole mergers form much more easily at low metallicity, and it drops by orders of magnitude as we move to solar-like metallicity environments. So This is something that acts like a filter that only cares about star formation that happened below a certain metallicity and uses that to produce black hole mergers. And this dependence is found theoretically. There's no good way to really probe this at low metallicity with observations in other way than gravitational waves. And as such, it's a result of many evolutionary processes acting together. But we can really understand where it comes from when we only think about the effects that are the most straightforwardly linked to metallicity. One of those I mentioned already. So stellar winds are weaker at low metallicity, and on average, this leads to tighter binaries with more compact objects than at high metallicity, and so easier to merge. More massive binaries are also thought to receive smaller natal cakes at formation, which helps the binaries to remain bound after their core collapse. And below a certain metallicity, what is common in our models is to assume that black holes can form with no natal kick and no mass loss whatsoever. So this increases the survival of binaries a bit further. And finally, a bit less easy to maybe hand-wavingly explain effect. This is related to the fact that the evolution of stellar radii depends on metallicity, and we find that this causes more stars to engage in mass transfer early in their evolution at high metallicity, and such interactions are thought to lead to more stellar mergers. So they, before double compact object is formed, so they are not going to produce double compact object mergers. I'm not really going to focus on other systems than black holes, but you can see that the typical dependence for neutron star mergers is much weaker. It's almost flat. They come from much narrower range of progenitors' masses, so they are not so affected by stellar winds. And black hole neutron stars fall somewhere in between in terms of this metallicity trend. Important note here is that while this general behavior that I just described is found by many groups using, say, different codes, and we qualitatively expect this to be the case, then how exactly it looks like depends on how we describe the evolution of massive stars in binaries. If I were to, for instance, change the metallicity dependence of stellar winds, parameterize it in a different way, then this would, for instance, affect the location of this drop. So it is somewhat uncertain. However, I like to think about this in the context of other transient events related to massive star progenitors. And when we put this dependence next to other transients that are linked to such massive stars, then it seems that there is this low metallicity preference seems to be a somewhat common feature. So I want to now explore a few consequences of this kind of dependence in my talk. And the first is kind of straightforward. So if we have this strong dependence, then if the amount of star formation that happens at low metallicity is uncertain, then this by itself adds uncertainty to the properties of black hole merger population. And I showed you the example of the merger rate earlier. But this metallicity dependent cosmic star formation history also affects the black hole mass distribution and its redshift evolution. So here you can see the primary black hole mass distribution of local mergers. And I'm comparing results obtained for the two star formation history, metallicity dependent star formation histories that I was using in the earlier example. Those are normalized by peak, so we can compare the shapes. And the difference is not dramatic in this case. But what I actually wanted to point out here is that when we ask about the fraction of those local mergers that come from high redshifts, then the two compared models give us very different answers, right? So the field part of this distribution is now showing contributions from binaries that formed less than 10 gigayears ago, redshift smaller than 2, say beyond the peak, below the peak of the cosmic star formation history. And in the red case, it's almost the entire population, while in the other case, well, you can see it's a minority, and basically all massive events in this case, we would say they come from beyond the peak of the cosmic star formation history. So this is a very different interpretation of the origin of those local mergers. And it also means that if, for whatever reasons, we were interested in the properties of host galaxies, of black hole mergers, then those also could be very different depending on whether we trust the red or the brown version of the universe more. Simply because in the brown case, galaxies have plenty of time to evolve in the meantime. So we could expect more massive and passive galaxies among the hosts than in the red version of the universe. So I would say that for the correct interpretation of gravitational wave observations, population properties of gravitational wave sources, having a model that describes metallicity-dependent cosmic star formation history is not enough. And we should rather aim to understand what is the range of assumptions that is allowed by current observations and should be considered in our models. This would give us at least some error bar that we can put on top of evolutionary predictions so that we can be more conclusive when we compare this with observations. And this brings me to the galaxies part of my talk. Because I think what makes it possible to answer that question is that, well, the fact that we now have huge samples of observed galaxies, and we know their empirical distributions of their properties, like the rate at which they are forming stars, the average metallicity, we know the galaxy statistics. So this allows me to fill in this metallicity, redshift, or look-back time plane with the number of stars that form in different parts, which is what we really need to start modeling populations. There are, of course, problems. The problem is that such observations are never complete. So we often miss faint galaxies. They can be intrinsically faint, such as low-mass galaxies typically are. They can be faint because they are distant or dust obscured. So we have to correct for this somehow. We also do not measure things like star formation rate and metallicity, but we have to rely on probes like UV flux or H-alpha flux and various emission lines. And translating this to the quantity that we want to use is not straightforward. There are different ways to do this, and they often lead to discrepancies. So those are the kind of factors that will non-trivially affect the answer to the question that I'm trying to answer, and I want to be careful about them to really understand what's the range of possibilities that I should consider. Now, I'm not going to really discuss this in detail, but somewhat separate category of issues here is related to the IMF, so the stellar initial mass function, which is really an assumption that we use in many different areas in astrophysics, and including when we analyze the light coming from galaxies to derive star formation rates, for instance. And we commonly assume that the IMF is universal, so it's the same across the universe, similar to the one in the Milky Way, but it may not be, especially if the star forming conditions are very different. So if the IMF was to depend on the environment, then this also non-trivially affects metallicity-dependent cosmic star formation history. But even if we forget about this particular part of the problem, the issues that I mentioned a moment ago are particularly important for the low metallicity part of this plot. So low metallicity tail of the birth metallicity distribution of stars. And I want to show this a bit better, so delve into some level of detail, and I will give you a quick tour over the problems with constraints on the low metallicity star formation history here. And I thought, well, I like to ask this question, what does low metallicity actually mean? And I actually asked this at a workshop a few months ago, and you can see some answers that I received here. So well, they differ. Some of those are very consistent with each other, but this was also a very specific crowd. But in principle, people think about different things when one says low metallicity. And this is fine because it should depend on the specific problem that we want to address or the model that we have. But let's focus on the SMC. So the Small Magellanic Cloud here. For now, let's look at environments with metallicities, SMC-like and more metal core, just because it's nearby, so we know a lot about this galaxy. And in particular, because it's so nearby, there are many different ways to observationally determine its current metallicity. And we do not have this luxury when we look at other galaxies, typically. And essentially only one of those methods that I listed here is to date applied to large galaxy samples. So that's the one that relies on H2 region optical emission line ratios. And those are mainly oxygen lines, so the metallicity that we derive that way is a good probe of the oxygen abundance, but does not necessarily tell us much about all the other elements. So let's keep that in mind. But using this method, we can at least put SMC in the context of all the other galaxies and compare it with the other environments to see where to look for similar metallicities. So let's look at one of the famous empirical scaling relations describing star-forming galaxies, the Mass-metallicity relation. And the question that we are facing here is really which one? Because that's not redshift evolution that you're looking at here. It's really, those lines are all Mass-metallicity relations that were derived at redshift 0. They are all based on H2 regions, but with different choices on how to translate the observed line ratios to metallicity. We do not really know which one of those is correct, which means that there is a substantial systematic uncertainty on the metallicity value that we derive that way. But here it is. We can more or less put the SMC on this plot, and you can see that we are really after low mass galaxies. Such low mass that they are often not even included in the figures that show typical properties of star-forming galaxies, like the star formation mass relation shown on the right now. So I hope that you can already see what's the next issue, which is that already at the SMC mass, those relations are rather poorly constrained, and even at low redshifts, we need to extrapolate to account for them. And if we want to learn about the amount of star formation that happens at low metallicity, well, we should not just ignore them, because it might be uncertain, but the number density of such galaxies is increasing towards low stellar masses. So that's the number density of galaxies versus stellar mass in this figure. And the slope at low masses is going up, meaning that despite the relatively low star formation rates of such galaxies, when we integrate this over the number and star formation rate, then this may still yield non-negligible contribution to the total star formation rate density. So, keeping all those caveats in mind, we can actually do this. We can use those relations between star formation rate, stellar mass, and metallicity, plus the number statistics to calculate that contribution. And you can see here that this gray band is the total star formation rate density, and the blue range is the estimate of the amount of star formation rate density happening below the SMC metallicity in the local universe, say. So we get some sort of an upper limit, say at most 10% of the star formation in the local universe happens below the SMC metallicity. But overall, it's quite uncertain, even at those low redshifts. And what about higher redshifts? So especially when we're thinking about gravitational wave sources, because of the potentially very long delay times, and second, because our detectors are getting more sensitive, so they are actually starting to observe sources at higher and higher redshifts. We can't skip this part of the problem, and we have to describe the whole cosmic star formation history. So not surprisingly, as we move to higher redshifts, we have to rely more on extrapolations. But there are two somewhat special issues that are important for this low metallicity relation that I want to highlight. And the first is that the method that we're using at lower redshifts, relying on optical emission line ratios from H2 regions, is not really possible to use it at redshifts higher than 3 or so, simply because those lines are redshifted out of the telescope bands. And GWST is clearly going to help here, so it's going to see those lines and will help us to map the metallicity evolution of the universe in a similar way as we do at lower redshifts, but we still have to wait for this. And the second thing is really a different spin on the question about which galaxies reionize the universe. So we do not really know well how many faint low-mass galaxies are lurking out there and whether they are reasonably star-forming, meaning whether they would follow, if we were to extrapolate the star formation mass relation down to lower masses, whether such galaxies really follow this relation, or maybe they are less star-forming. So those are the open questions that really affect the result at high redshifts a lot. So you can see this is essentially the same figure as before, but now I extended this to much higher redshifts, much stronger look-back times. You can see the blue range is growing, the gray band showing the total as well. So, but if we are looking at the amount of star formation happening at low metallicities, that this is telling us that this is somewhere between almost everything to below 10% of the total. And now I also derived this estimate based on mostly oxygen abundance measurements, or at least metallicity measurements that are sensitive to the oxygen abundance, which is really not ideal when we're thinking about massive stars, because their evolution is mostly affected by the iron abundance. That's what's driving stellar wind mass loss, is mostly driven by iron elements like opacities. So, and if I were to derive this estimate using iron-based metallicity rather than the oxygen, it would not look the same, because the two elements are not released to the interstellar medium on the same time scales. They are produced mostly by two different types of stellar sources. So while oxygen is abundantly produced by core collapse supernovae that happen promptly after the burst of star formation, then iron is significantly contributed by type 1a supernovae that, similarly to gravitational wave sources, come with a certain delay. So the iron production is lagging behind. And it's difficult to repeat the exercise that I did using oxygen-based abundances, because we don't have many galaxies for which we know the iron abundance in star-forming materials. And nonetheless, I'm trying to say something about that, but this is work in progress. And now let's step away from those details about galaxies, properties, and let's look at the bigger picture. So let's try to put all those pieces together. So I just argued that low metallicity star formation history is particularly uncertain, and it's difficult to constrain with electromagnetic galaxy surveys. And when I put this next to the predicted low metallicity preference of black hole mergers, then, on one hand, this is a very unfortunate combination, because this uncertainty on the left means that does not allow us to accurately predict black hole merger properties, no matter how well we understand the massive star evolution and this right part of the slide. But on the other hand, it means that black hole mergers are potentially great probes of star formation happening at low metallicity. And here we are looking again at the low metallicity star formation history with the different literature assumptions that I showed you at the beginning, but I added this gray band. So this indicates, using the same metallicity cut, what is the range spawned by my observation-based estimates. Well, you can see that it is narrower than the range of assumptions that were used in the literature, but it's still fairly broad, and it's probably broader than what we would like it to be to learn about massive star evolution from gravitational wave observations. So here you can see, if I were to use the extremes of that range that you can see now in the bottom panel to calculate the black hole merger rate as a function of time, then this is shown in the top panel. There's, I can basically repeat what I said earlier. There's still almost an order of magnitude difference. Notice the shapes differ, and also notice that there are some similarities between the two panels. So if you look especially at the peak locations, then you can see, this is a quick way to illustrate that constraining this top figure is one of the potential ways where gravitational wave astrophysics can help us to understand something about the low metallicity star formation history in this case. Now, you can see that the differences are the biggest at long lookback times, and we are not reaching there yet with gravitational waves, but that's why I said I'm excited about the future detectors, because this will be well within their reach. So they are going to map this entire figure, and we can go a bit deeper into the details and look how this metallicity-dependent cosmic star formation history is affected by different properties of star-forming galaxies that are poorly constrained by current electromagnetic studies. And if you can see in gray lines in this figure, you can see that there's differing slope in peak locations. So those are the kind of factors that we can potentially constrain with future gravitational wave observations. And they encode some information about the uncertain galaxy properties. So this is a very different tool that we can potentially use to study chemical evolution of galaxies. It's very different than taking a telescope, pointing it towards a galaxy and observing light. Here we need to model population of gravitational wave sources, and this encodes some information about how the universe is evolving, how the chemistry of evolution of galaxies sits in there. I can look at the mass distribution again. So this is the redshift 0 primary black hole mass distribution of black hole mergers. And now I used the extremes of my range to calculate this. And contrary to what you could have, what I showed you earlier, there's no differences in the shape. And so you can see that the shapes differ at the high mass end. And this is where low metallicities is actually important, because while this low mass black holes can form, let's say, an emetallicity for the high mass tail, we really need to avoid this strong mass loss in stellar winds. Or as an alternative, we need to involve dynamical mergers where we can stack many black holes together and grow their mass that way. This will also evolve with redshift in a way that is sensitive to the metallicity-dependent star formation history. So while the locations of the features, we can predict this with the stellar evolution, and then how this evolves with redshifts is also very sensitive to how the star formation history, how the metallicity-dependent star formation history looks like. I will skip this, but Lika did a nice work to show how this distribution would vary depending on how we vary the shape of the metallicity-independent star formation history. So I'm starting to lose my voice, and this was already a long story with quite a bit of details. So let me zoom out a bit and summarize this. So gravitational wave astrophysics, I think, is not only about the evolution of massive stars in different environments, in isolated multiples or dense clusters. To understand the origin of the observed sources, we have to remember about this third part, the equally important part of the puzzle, I would say. And it seems necessary to better understand chemical evolution of galaxies to make progress in this area, to understand, if we want to dig into the details of stellar evolution, binary evolution with gravitational waves, then really we need to narrow down the uncertainties on the other side. On the positive note, double compact object mergers can be used as probes of galaxy chemical evolution, and black hole mergers seem particularly interesting because they seem to care about especially those galaxies that we normally miss, or we only start to uncover them, but so far we are doing this with very different tools, with very different biases than gravitational waves. And I think that in between those fields, there is still some unexplored area for future studies that will grow with improving detectors and new facilities on the horizon. With this, I would like to thank you for your attention.
Thank you very much. Thank you, Martyna. Questions?
So I have a few questions. So first is that in your mass distributions, your highest masses in the distribution stretch out to 35 40 solar masses, while the distribution of primary masses in the observation goes all the way up to about 80. So is that a problem or not? So
yes, well, for the pure stellar binary evolution channel, we start to struggle above a certain mass, as you're surely aware. We have something like pre-instability mass gap, where stars, well, we stop producing remnants because stars above a certain mass reach certain conditions in their interiors where they start producing pairs that eat up support, like the stars start to lose radiation support, and we predict no remnants. The exact mass above which this happens is somewhat debated, but I would say, yeah, around 50 solar masses is probably where the lower limit of this gap is now. So if next observing grounds really show that this distribution is stretched up to higher masses, then this is a hint that dynamical channels operate. So the other part of the answer is that I picked one example model of stellar evolution that I stick to throughout my talk, so there's more room for different variations of this distribution.
So when we talk about different channels, I think that then the conclusion that the merger rate history should tell us a lot about the star formation history. It depends crucially on the assumption if there is a single or more than one channel as well, because if we have the dynamical channel with larger efficiency and a different star formation rate history, the black hole rate history may have two peaks that will correspond to different peaks and different phenomena. So this may be, the story may be much more complicated than your.
Yes, but I think, you know, this is part of the problem, and this also means that in principle there's more to learn, because Global cluster star formation history is also not very well known. So if we can, looking at the population, I mean, we will have more information to study. We'll get redshift evolution of the different properties of the sources. We have more sources than just black hole mergers. Those are the most interesting for me because of their strong metallicity dependence, but we have other sources. In principle, we should predict all the observables and look at them at the same time. Also stochastic gravitational wave background. So combined all this, I think we'll have much more information to disentangle those different effects. And yes, so one of the signatures of more than one channel operating to produce black hole mergers is that we have some peaks in the redshift merger rate evolution with redshifts, where one could be attributed to either dynamical channels or maybe chemically homogeneous evolution that also has potentially very different dependence on metallicity or population-free stars, who knows? Yes, it's of course it's much more complicated, but I'm organizing a workshop to dig into those nasty details. It should happen next year. So.
Okay.
Any more questions? Check on Zoom. I don't see any. So other galaxies nearby, apart from SMC, right? They have a range of metallicities, right? Are they useful?
So are they useful? Yeah. Well, in terms of where we can try to constrain stellar evolution in somewhat detail, then SMC is the current limit. It might get a bit better with the ELT, but I'm not an observer, so I'm not going to tell anything more about that. But also, like some of the other galaxies that are reasonably nearby and are low metallicity, people looked at them trying to search for stars that they can use to study things like winds, for instance, in some detail. But it turns out that, when we are deriving metallicity based on the oxygen abundance, then that's not the information we need to really decide whether this is interesting galaxy that extends this metallicity ladder to lower metallicities. And actually some of those turned out to be fairly SMC-like in terms of iron abundance over time. So we also have to care about how we derive abundances and what elements we're actually looking at.
The nice thing about these nearby galaxies, especially SMC and LMC, is that we know of binaries there, right? From variable stars. This is probably the only, this is as far as we can get. Probably we might know about some binary systems as far as M31, but not further than this. Is that useful at all? There are some systems of massive binaries which have been studied in detail.
Yes, so yeah, I mean, this is interesting, but at least this talk is really talking about the populations and how much we can extrapolate from one system to the entire universe, or like all the environments with similar metallicity even is always a bit of a question mark to me. But surely there are very interesting studies that we can do with stars and multiples we find in LMC. I think that was the one where we found some systems with one system at least with a black hole and a massive star. So yeah, that's certainly interesting. And I think, to disentangle all of those different effects that we have to think about when we look at populations, we also need to think about other ways to constrain the different pieces of the problems. Yeah.
Okay. I don't see any more comments, so let's thank our speaker again. Thank you all for coming.